All right, so now we're going to talk about direction indicating instruments. One of the most commonly used methodologies for direction indicating instruments, pre-GPS, pre-WAS, and all that good stuff, was simply the gyros. A gyroscope implanted into the lunar module's computer took astronauts all the way to the moon. You can hear them referring to it if you watch the movie Apollo 13. They talk about floating close to gimbal lock. We're going to find out here in a second, but the gimbal is the ring in which the gyroscope is mounted. It's a core component of it. And if you were to align all three of the gimbals inside of the lunar module's IMU, they would get like synchronized, and they wouldn't do its job anymore. Effectively, it would render it totally useless, and then they wouldn't know exactly which way the spacecraft was pointed. Now, that is state of the art in 1969. Actually, 13 would have been like 1970, I believe. But that is that's the prevalence of gimbals in aircraft. Now, we like on the OH-58, which is another older airframe, we had three gyros that sat right behind the co-pilot seat, and they sit about your hand. They sit about that tall, and one of the first things that we would do is get them spinning. Once they were ready to go, we would align the inertial navigation system, and what that's doing is the gyros are saying like, hey, look, the helicopter is pointed in this direction, at this altitude, with this flight attitude. It basically says, hey, look, the helicopter is sitting like nice and easy, just like sitting there ready to go before it takes off. So it's just sitting on the ground, right? And the gyros say, hey, look, we're pointed at 180, and we don't have any tilter or pitch or yaw or anything else like that. We're just sitting there like just nice and level, not really going anywhere. And that's what our zero mark is. So we're saying like that's normal. Now, the moment the helicopter lifts up and goes forward, it starts logging the way that the gyros will tilt back and forth, or so on and so forth. And it says like, hey, look, we went forward for so long, and then it could take the air data information and say like, okay, we were going this speed for so long, and which we were tilted this way. So then we can infer that we flew 100 feet. And then on the map, it'll say like, okay, we knew where we started at. We knew that we flew 100 feet. And we knew the direction that we went, because also the helicopter turned as it flew, and it knew that it was at 180, then it turned to 360 and went that way. Or I guess that would be 270 if you want to be correct about it. So we know we turned to 270, and the other gyro who's logging all this information on the directional plane on that horizontal axis, it says like, hey, look, it also turned, and it turned for this long before it turned back. And so now it knows which way it flew, how far it flew, and the orientation that it flew at the very, very end. And then you have another gyro knowing that its altitude, that it also came up for so long and went over, and it also bounces that off of all the air data stuff. So that's an old school way of doing it. Now you'll see this is still employed, even though it's more advanced than what it used to be in inertial navigation systems, or INS. You'll hear INS, or you hear Air Data Inertial Reference Unit, or ADIRU, depending on who you ask, on heavy commercial airplanes. There's usually two of them. Then, like, one of the first things that you do as you're pre-flighting the plane is that you're going to turn the plane on. You're going to get the LRUs or the ADIRUs to align, and all that's doing is saying like, hey, look, the gyros are spun up, they're ready to go, and they're going to say like, hey, look, we know this is where we're at. This is like all the information we have right now is piped into the ADIRUs, and then you're going to give it a GPS fix, and you're going to say like, hey, look, this is where the nav computer says we are at, and so we're going to put those coordinates in, and it says like, okay, cool, like I know where I'm at on the map. So that way, if everything else fails, you at least have your internally closed off from the rest of the world system to tell you where to go, and that's being used today. Now they don't use the old electronic motor spun gyros, and they definitely don't use steam gauges like vacuum pump driven gyros. Instead, they'll use laser ring gyros, which we'll get into here in a minute as we kind of break into it. But I will tell you all that on the front end to just so that way you understand how important the gyroscope is to aviation. It's one of the things that is extremely or has been extremely kind of like a bedrock of instrumentation. It's one of the things that that's somewhat unique to aviation, that you can find a lot of the things that we'll put on airplanes and cars. Really is like kind of a car for the sky. A gyro is not one of them. A gyro, the only other place I've ever seen gyros be used outside of things that fly, and that's also missiles and all kinds of other stuff, spacecraft, but is on ships. So sometimes you'll get the same thing on ships. And the reason being is it's simple, is that like if you start from a known point, you spin up a gyro, then you can just log all the movements of that gyro and know where the vessel has gone. And it's self-contained, and it is an extremely robust form of navigation. Now, let's talk about what a gyro is. So I'm going to put a graphic up, and we're just going to talk through it. So this is out of the 8083, and we're just going to go through A through D, and we're going to talk about what every single one of these is doing. And I'm just going to read it off, and we're just going to kind of talk our way through it. So a mechanical gyroscope or gyro is comprised of a wheel or rotor with a mass concentrated around its perimeter. The rotor has bearings to enable it to spin at high speeds. All right, stop. So all the gyro is effectively is a wheel. Like it is a wheel that is basically kind of like blown out on the ends. So if you were to take like an old quarter, if you ever made one of those quarter rings where you take a quarter and you take a spoon, you tap it out and it flares the ends out, so that way you have this like almost like I-beam kind of shape around the edge of the quarter. That's what gyro is. And the reason being is that like you can, if you put all the mass of the wheel on the outer edges and flay them out like that, it spins a lot easier, a lot smoother with a lot less force. So that way it reduces the amount of energy you have to put into it to keep it up and keep it going. But now what it's going to do, it's going to spin, but it can't just spin. It has to spin at an extremely high rate of speed. And the reason being is that if you think through physics, all right, you have a wheel that's spinning, okay? As that wheel spins, the angular momentum of that spin is going this way, all right? Now, what tells us that there's a right-hand rule with torque, that is that if something spins forward, the torque wants to act to a 90-degree off to the side, like so, all right? So if there's old physics trick that you take a bicycle wheel, you suspend it from the ceiling and you spin it, eventually it'll raise up and turn like that. And the reason being is that because the torque, as the bike spins like this, the torque is pulling down, and the way that those vectors work, so you have a force going this way and then force going straight down, is it starts to peel it off to the right and cause it to stand up straight like that. That's the basic principle of a gyro. All right, so on B, it says to suspend the rotor for rotation, the axle is first mounted in supporting ring called a gimbal. So remember when we talking about the Apollo astronauts getting all freaked out about gimbal lock, that means that all those gimbals are lined up. And once they're lined up, they're synchronized, and you can't unsync them without like shutting the whole thing down and starting all over. But you're in space, you can't do that. So that becomes a challenge for them. So if you look at B, you have a ring that goes around, and then that wheel is suspended inside of the ring. So that wheel is spinning super, super fast. The ring is stationary. It's just holding the spinning wheel, all right? Now we go down to C. If the brackets are attached 90 degrees around the supporting ring where the spin axle is attached, the supporting ring and rotor can both move freely 360 degrees. When in this configuration, the gyro is said to be a captive gyro, so that's the C graphic there. It can rotate only one axis that is perpendicular to the axis of spin. The supporting ring can also be mounted inside an outer ring. The bearing points are the same as the bracket just described, 9 degrees around the supporting ring from where the spin axle is attached. The attachment of a bracket to this outer ring allows the rotor to rotate in two planes while spinning. Both of these are perpendicular to the spin axis of the rotor. The plane on the rotor spins in due to its rotation about the axle and is not counted as the plane of rotation. So on D, a gyroscope with this configuration, 2 rings plus the mounting bracket, is said to be a free gyro because it is free to rotate about 2 axes that are both perpendicular to the rotor spin axis. As a result, the supporting ring with the spinning gyro mounted inside is free to turn 360 degrees inside the outer ring. So, what does that all mean? That means that as that wheel spins, all right, you have something that is effectively gets hung up in in space and time. It's spinning. It's got this angular momentum that's kind of keeping it in a singular orientation. And then because of the way the gimbal rings are attached, so you have a wheel with a gimbal ring that's attached to it, and then you have on the outside of that gimbal ring another ring where it can actually, that whole apparatus can move inside of that ring. And then you'll have another ring that can make sure that apparatus can move. So effectively, that gimbal or that gyroscope now basically just sits in one spot and it just holds its position. As long as it maintains its spin, then it'll basically always be oriented in a certain direction. So all you have to do is just keep it going, and then you'll keep the initial reference point from wherever that aircraft took off at. So if you have a gyro and you spin up that gyro and you orient it and you say, like, this is point number 1, this is direction number 1, this is altitude number 1. You have all three dimensions of space, and it's oriented to a certain place, right? It's spun up, it's going, and then all of a sudden you move the aircraft. Well, as long as that thing stays spinning, it's going to stay in that orientation. Doesn't matter if you go up and down or side to side or backwards or forwards or upside down or whatever else. That gyro is going to keep on just going the same direction that always was. And then the rest of the housing of it all will rotate around it. And that's really, really advantageous because that allows you to always say, like, hey, look, this is where the orientation was whenever we started. This is what our orientation is now. How did we get here? And then it'll turn around and say, like, hey, look, this is how we got there. And so since we know how we got there, we know where we are. Now this can start making you go cross-eyed. There's like an old missile video that you can watch that talks about this, and it's basically somebody reading the code that the missile is running. The missile says, like, the missile knows where it is because it knows where it isn't, and it just keeps on looping that way, whatever else. And what it's doing is it's basically saying, like, hey, look, what does my internal INS or my gyros tell me that I'm doing? And then like what, where can we eliminate the things that we are not at? Therefore, we must be at this one place. And then it starts all over again. Okay, now we've moved again because we're like a missile, we're flying super duper fast, and this is all happening really fast. And it'll say, like, okay, well, where can we not be at? Okay, and then we must be here, and it keeps on doing this. But the way it's doing it is pulling that data from its INS system on board, and it says, like, hey, look, like, I know where we were and I know where we're not. So therefore, this must be where we are now. So that's gyros. So they can be really, really complicated. So now let's talk about, where do we see gyros inside of the airplane? Okay, so there are 4 gyroscopic flight instruments that we want to talk about today. The first is going to be the attitude indicator, or the artificial horizon. Now, this is a gyroscopically driven instrument that basically says, hey, look, whenever it starts going and the aircraft is on the ground sitting nice and level, you'll see the artificial horizon kind of dip down whenever it's not running, and then the moment that you crank the engine and the vacuum starts sucking on it, it'll stand up and get level. And then your job as a pilot is to grab the little airplane and orient the airplane to the horizon. And what's going to happen is, whereas the gyroscope is going to keep that horizon nice and level, and as the plane flies around, like, it's going to stay in one spot, and the plane's going to fly around that horizon and give you an idea of, like, where the airplane is oriented. Now this is really important for like instrument flying, and so like if you want to make a nice coordinated turn, this is one of the instruments that you look at to know the turning radius or the rate of turn that you have, or the rate of pitch up or down or roll or whatever that's going on, because that airplane is going to stay in the same spot, and the horizon on the backside is going to move around to kind of give you an idea of how the airplane is oriented. The next one is going to be the heading indicator. A heading indicator is going to look like a compass, and in fact, it can kind of get confusing with some of the compasses that are out there that are vertical rather than the regular old float compasses. But the heading indicator is fundamentally different. It's gyroscopically enabled, and it's basically like once you get the engine up and running, you're going to align that heading indicator to wherever the compass is heading. So if you're sitting, the airplane's running, and you look and you see you're at 180, and the heading indicator's all off, you're gonna grab the little knob and you're gonna spin it, and you're gonna spin the airplane all the way to 180, so that way it's aligned with your compass. Now, as you fly, there's a condition called precession. We're going to talk about that here at the end of all of this. That you'll have to make adjustments. The only time you can make adjustments to it is that if you're in straight and level flight, and you're not adding power, you're not taking power away, you're not climbing, you're not diving, you're just sitting there, just going, just going straight. Then that will give you the right conditions to align it. It's also a thing that you'll do before you take off, because that's the last chance you're going to have to make sure that thing's aligned. So if you're going to navigate with it, you need to make sure that it's lined up with the compass, so that way it doesn't take you off in like Timbuktu because it was aligned incorrectly. But that is another gyroscopically enabled flight instrument. Another one is the turn and bank indicator. So the turn and bank indicator is basically going to be like a little airplane that is going to rock one way or the other with a little ball. And so what that's doing is telling you, like, if the airplane is turning, the direction of turn will dip the wing down on the turn and bank indicator, showing you that the airplane is actually coming around and banking that way. Now the ball will swing one way or the other based on whether or not the turn is coordinated. So if you have a nice coordinated turn, that ball is going to sit right there between the two hash marks, and it's going to let you know that you're making a nice coordinated turn. And then we can math out like where that turn is going to come out at. If it's nice and coordinated, we know that it's a standard rate turn, and the airplane is turning at such a speed, so on and so forth. Now, if it's not coordinated, then that means that our airplane is either skidding through the air or it's slipping, one or the other. And sometimes you want to slip, but most times you don't, especially if you're just flying around in the clouds and you're trying to navigate. You want to have a nice coordinated turn. So that's what it's there for. Now the ball has nothing to do with the gyroscope. It's just simply like a level, like a inclinometer, like you'd have in a truck that's like doing some off-roading or something. But the gyro behind the turn and bank indicator absolutely is gyroscopically enabled. It knows what straight and level looks like, and then as you roll the plane one way or the other in the turn, it's going to indicate that as you go. Okay, so gyros are historically run through what's called vacuum pumps or vacuum power. Matter of fact, older airplanes, when you crank them up, one of your checklist items will be like, what's our vacuum at? And you'll even pull the power down to say 1,800 RPMs and check your vacuum gauge, make sure you still have vacuum power going, even though the RPMs are reduced. Now, all that is that there is, on the backside of the engine, there is a little vacuum pump. And all it is that. It's just basically, it sucks air in and shoots air out the other way. It's a centrifugal type pump that does exactly that. The air enters in through the cockpit through a filtered or like internal cockpit filter that can make sure that it's clean air, because that air is going to go through the pump and then into all the instruments, so you don't have dirty air, because that's going to have multiple levels of failure if that goes bad. Anyways, so the air enters in, goes into the pump, gets pressurized, and then gets pushed into the vacuum system. The vacuum system is going to have little air lines that go into the instruments, and that air spins, or will spin the gyros on these older instruments. Now, and then you'll even hear them up whenever you crank an engine or you shut them down. You'll hear them going, spinning down as they slowly kind of attrit all that momentum that the vacuum pump has imparted to it. Now that allows the gyros to spin, and you'll even see it as you crank the engine, and as the vacuum pump hits it, all of a sudden all the gyroscopic instruments will jiggle and jump up and be all ready to go, and then you'll start to orient or align like all your heading indicator and all the other good stuff. And so that's historically the way that aircraft for a long time flew, is off of vacuum. Now here in the past, several years, there's been a step away from vacuum pumps. Now, why? No, it's pretty simple. The vacuum pumps will fail. There's a reason why you check it on a regular basis. If you're flying in IMC or flying instrument conditions, and then all of a sudden your vacuum pump fails, or there's some sort of vacuum failure, line cracks or filter gets clogged or whatever the thing is, then that could affect a lot of your flight and navigation systems, and you don't know, you're just flying blind at that point. You don't know where you're at, and you could be like up in the Rocky Mountains inside the soup trying to come into Denver. All of a sudden your vacuum pump fails, and it's like, well, we don't hit a mountain, because that's a real possibility down there. It's even a real possibility here. There's all kinds of antennas and stuff as you fly into Texarkana, and if it was like soupy and you're trying to come through all those clouds and stuff, and you're expecting to be in one spot, but the vacuum pump it fails on you, then you don't know where you're at. You could be in like a serious condition there, and you don't know what you're going to hit. So it's real important that that thing works. So a lot of people said like, hey, look, what is more reliable and more redundant than the vacuum system? Now, with a vacuum pump, if you have a twin engine, you might have two vacuum pumps, but most of the time you only have one tied to an engine. So you're kind of betting all your flight instruments on that one vacuum pump. Well, they came around and then they started to put electric motors in them, or they started using electricity instead. And they said, hey, look, like if we have an electrical failure, we have a couple of different ways to generate electricity. We have a battery if we absolutely have to. We have the coils on the engine that will generate, or not coils, but like on those engines. But like we have a generator on the engine that will generate power and backfeed it into the cockpit. So we have multiple ways to get electrical power to the instrument, so that gives it a little bit more safety. And if there's a failure, it's more likely that an instrument will fail and not the entire system will fail. And so the kind of moving towards all electric has been a thing, and it will continue to be a thing for a while. That like slowly but surely all of the vacuum systems will just kind of like go away. It also helps reduce complexity in the engine, because you don't have a vacuum pump, you don't have all those vacuum wire or lines coming into the cockpit and all that good stuff. So it's just all around, it's just a better system. But so like how do we use electricity to work a gyro? So let's talk about ring laser gyros. The ring laser gyro is widely used in commercial aviation. The basis for RLG operation is that it takes time for light to travel around a stationary, non-rotating circular path. Light takes longer to complete the journey if the path is rotating in the same direction as the light is traveling. And it takes less time for the light to complete the loop if the path is rotating in the direction opposite of the light. Essentially, the path is made longer or shorter by the rotation of the path. This is known as the Sagnac effect. So essentially, very similar to the gyros, but instead of having a spinning wheel, you have a spinning ring of light. And then based on the movement of the aircraft, you're either compressing or expanding the path in which the light has to travel. They then can calculate how far the aircraft moved based on the change in speed of completion of that circular course for the laser. And it says like, hey, look, we are 10 feet to the right because the laser took a little bit longer to come around. And that's how we do laser ring gyros. However, the ring laser gyro, while it's great, it still takes up space and it takes up weight. Even though like you've gotten rid of a lot of the challenges that come with mechanical gyros, you still have a gyro that's like so big that you end up having to find a place for. You still have to. It takes up floor space. It takes up cabin space. And so there was an incentive to see if we can make it even better. And they figured out how to do it with a MEMS system, a micro electromechanical system, MEMS. Now, basically, nowadays you can get gyros for like Arduino kits and stuff that fit in the palm of your hand, that they're about the size of a quarter. We'll put some pictures up of them so you can see. And that kind of becomes the basis of what modern gyroscopes still will use. Now, you as a mechanic will have to be familiar with like kind of all three different flavors of it. You have like the old mechanical suction driven gyros, and then you have like the laser ring gyros that you'll see in kind of like they're kind of in that intermediary like 1980s to the early 2000s kind of technology. But nowadays the MEMS gyros are actually pretty common. Like, matter of fact, if you were in our Tango flight program and you built the RV-12IS, it's going to have a MEMS gyro mounted to all of its gyroscopically driven instruments that go into the panel. That's by far going to be the most common one going forward. But until a lot of those old aircraft either get converted or retired or crashed or whatever, that's just those old vacuum driven pumps and stuff like that are still going to be around for a while. And so you need to kind of understand the nature of gyroscopes and kind of like the different flavors that you might have to come across. Now let's talk about something we haven't talked about yet, and that's going to be precession. I'm going to give you kind of the let's see if we can get you the All right, here's the book definition for precession. So precession is a second important characteristic of gyroscope. By applying a force to the horizontal axis of the gyro, a unique phenomenon occurs. The applied force is resisted. Instead of responding to the force by moving about the horizontal axis, the gyro moves in response about the vertical axis. Stated another way, an applied force to the axis of the spinning gyro does not cause the axis to tilt. Rather, the gyro responds through force was applied 9 degrees around in the direction of the rotation of the gyro rotor. Okay, so what does that mean? That means that if you have a gyro that's spinning, and I were to take it and say if I were to push up right here, it's not going to do that. Because of the rotational force and the vector thing, it's going to pitch up like that. So I push up here, it'll pitch up right there. Now, this may seem like some kind of like woo-woo craziness, but it makes sense when you start to think through like all the different vectored forces that could potentially happen with a gyro. And you can absolutely see it in the flight controls of a helicopter. If you start going and you look at like, okay, well, like I'm going to pull back on the cyclic and I'm going to push the swash plate up here, but you start looking at it like there's all these weird angles like in the flight controls. You're like, why is that? And it's because what they're doing is they're accounting for the gyroscopic precession. So that way, whenever you pull it, like you nose forward on a helicopter, if you rigged it straight through and there was no like accounted for angle differences, you would go to the left. Like so like you go, oh hey, whatever. So what they've done is they said like, okay, like if we have a forward cyclic motion, well, we need to actually put the input in on the right side and slowly bring it around so that way it will hit 9 degrees, so that way the flight controls are rigged appropriate and they're aligned that way. Now with instruments, we have to take that into account as well, that like, hey look, like if this is going this way and we're pushing on the gyro like to the right, then it's going to show up forward, and we have to, most of that gets accounted for in the math, the way that the computer or the device interprets the data. Now where it starts to matter is that like the precession can start to manifest in all kinds of like weird ways in the interface that you're looking at. For instance, as you're flying with a heading indicator, it's going to slip off and go off mostly to, usually in my experience, they seem to always go to the left. And so, but like I guess it could go to the right. I don't know if there's any reason why it can't go to the right, but just in my experience, it always seems like I'm turning my plane back rather than going this way. And so you'll have to constantly try to like make little adjustments to your vacuum driven, your own mechanical gyros on a regular basis. The electric stuff, you don't have to worry about it. But like with the older stuff that actually has physical things that are moving, well, I guess they're all physical. The other ones are lasers, which doesn't feel quite as physical. But the old mechanical gyros, they will always be off a little bit, and you'll constantly have to be like, playing with it. So like anytime you're getting straight level flight, this is kind of a good thing to just like scan your instruments and see like, okay, well, like the heading indicator's off, so let's fix that. Oh, the artificial horizon's off, let's fix that. The turn and bait coordinator doesn't seem to, you don't have any sort of anything to really worry about that. It's just either it's going straight or it's left or right, one of the two. Just precession doesn't seem to bother it as much. The other two absolutely does. You're constantly like fiddling with it to try to make it right. Now, on the MEM system and stuff like that, you don't have to deal with precession as the pilot. It's taken care of inside of the machine itself. Yeah, so that's precession.